with the orthogonal polynomial singular integrals and solving Riemann-Hilbert problems numerically.
All right, thanks. So this course is on, well, I guess what the title says. We're going to look at how we can solve Riemann-Hilbert problems numerically. I'll discuss some applications to Wiener-Hopf problems, just vague applications, really. And this is sort of building up numerical methods that I developed in sort of 2010, 2011. But we're also going to see how they've been revamped in sort of more modern terms using the Julia programming language. So all of this is available open source, and I'll demo it in a second. All right, so I guess I should start by defining what a Riemann-Hilbert problem is. Okay, so we're given an oriented contour gamma in the complex plane, and it can have multiple components. It could have, say, loose endpoints. It could have rays going off to infinity. Let's say multiple junction points. So this would be an example of a fairly complicated gamma. All right. Then on gamma, we're given two functions. Let's call it f and g from gamma. And these are matrix-valued functions. So we're dealing with matrix Riemann-Hilbert problems. So what's the problem? The problem is to find a function phi defined off gamma. So a matrix-valued function such that it satisfies the following four properties. One, it's analytic. So each component is analytic in the complex plane apart from on gamma. Two, it satisfies some asymptotic condition. So for example, phi of infinity is equal to the identity matrix. That's pretty typical. By phi of infinity, I mean the limit as z goes to infinity. And three, on gamma, so for a point on gamma, let me draw a picture. Here's say the point S. We have, say, two limits, one from the left and, say, another one from the right. And what we're given is the relationship between the left and right limit of phi. So we have, I guess I can use my colors, phi plus of S minus g is one of our given functions. Is equal to f of s. So basically, given f and g, we want to recover this analytic function phi. Okay. Now we're not going to do this analytically. We're going to do this numerically. So we're going to see how do we solve Riemann-Hilbert problems like this numerically.
I'm going to ask a question. So are you allowing your contours to go off to infinity multiple times? So you
yeah, why not?
And in every one you want phi to go to the identity at infinity.
Yeah, we're thinking of this as just defined everywhere off the contour. We're not. So that's sort of the point of you can have loose ends. We're not thinking of this as phi1 in this sector, phi2 in this sector, phi3 in this sector. We're thinking of it as phi of z defined everywhere off the contour. And then now normally the jump tends to the conditions are normally such that you can have a solution that has the same asymptotic behavior regardless of how you go to infinity. So All right, so let me just give some examples that we're going to use. These are fairly simple examples. So example 1. Now I'm not really from the Wiener-Hopf community, so these examples are going to mostly be from the integrable systems community that uses Riemann-Hilbert problems quite a bit. The first example is the Hastings-Macleod solution to Pan-Levade 2. Okay. So basically, Pan-Levade functions are functions that solve nonlinear ordinary differential equations, but it turns out that they can also be recast as Riemann-Hilbert problems. So what's Pan-Levade 2? Pan-Levade 2 is basically a nonlinear version of the area equation. Okay. Now this is a second order differential equation. We have families there's many solutions to this. The particular solution we're looking for behaves asymptotically like the area function as x goes to infinity. Okay. So what's the connection to Riemann-Hilbert problems? Well, the point is that all solutions of Pan-Levade 2 can be written in terms of solutions to Riemann-Hilbert problems. In the case of Hastings-Macleod, it's a fairly simple one. Of our contour gamma consists of 4 rays. We have I forgot to mention this is what we call a left Riemann-Hilbert problem because the G is acting on the left. You can also have it acting on the right. So on this contour gamma, we have so there's no F. We just have a G. We're given G. We want to recover phi. What's G? Well, G is very simple. It's just 1, 1, I, e to the I theta of s. I'll write down. So this is a 2 by 2 matrix problem. These are lower triangular matrices. These ones are upper triangular. And then okay, where theta of s is 8 over 3 s cubed plus 2xs. Okay. So here x is the same x as there. X is a parameter in our jump. For any specific x, we have a Riemann-Hilbert problem. Then the challenge becomes, given these jumps, these g of s's, recover phi analytic off it. And if we can do that, then we can recover u, the solution to the nonlinear differential equation, from phi. From the 1, 2 component.
Is this a parameter on the ray?
What's that?
Is that a parameter on the ray?
Yeah, s is the variable for the. I'm using s when we're on gamma, z when we're off gamma. Okay.
I'm using it as a real.
No, it's not real.
Oh, it's just. Okay.
So theta of s is. Yeah. Okay. I'll just do 2 more examples. Example 2, defocusing nonlinear Schrodinger equation. This one has just a single contour gamma, so this is maybe closer to classical Wiener-Hopf things with the jump 1 minus e to the minus I theta s r of s e to the I theta of S1 where theta of S is whatever 4ts squared plus 2xs. Okay, so here we have two parameters, x and t. We have a Riemann-Hilbert problem on the real line. If we can solve this, we can recover NLS, solutions to NLS, by essentially the same thing as there. Z phi 1, 2 of Z. Here I mean the 1, 2 component.
Sorry, what was your 1, 1 element? You can't read it.
1, 1 is 1 minus absolute value R. So R it's something called the reflection coefficient. Which is usually nice. So I won't really, I'll give an example later, maybe on Friday. But basically, if you're thinking of for any initial condition for NLS, NLS being the PDEs ut plus uxx minus 2 absolute value u squared u is equal to 0. So basically we're solving this time evolution PDE. Given an initial condition, we can find a reflection coefficient, essentially nonlinear version of the Fourier transform, create this jump, solve the Riemann-Hilbert problem. Once we solve the Riemann-Hilbert problem, and the nice thing about this is the t and x dependence are trivial. So it sort of trivialized evolution of this nonlinear PDE. We can solve the Riemann-Hilbert problem, recover phi, and from phi get the solution at any t and x. Okay. So my last example is is sort of the classical Wiener-Hopf example, where now our contour is something like this, and our jump, in this case, we have phi plus of s minus, it's just a scalar, minus I square root, I guess it's normally called gamma, phi minus of s is equal to f of s, where this is square root k minus s square root k plus s times I, and this is some function minus k sine theta over s minus k cos theta. So k and theta are parameters. If we solve this, we can solve Helmholtz off the half plane. Here this has it's only scalar valued. You can do this for matrix versions as well. Here this has some difficulty in that the solution itself only decays like 1 over square root k. But it sort of fits into the framework of problems we want to solve. Okay, so let me switch to the computer, and so now that we have an idea of what kind of problems we want to solve, I want to just show that we can, so the question is, can we solve them numerically? The answer is yes. So let me I'm going to take this example, Hastings-McLeod solution, and show how it can be solved in this software package. So this is is a Julia package called Riemann-Hilbert.jl. So here I'm just loading the packages. Now the first step is we want to set up our contour, which consists, now the true problem has infinite rays, but because of the exponential term, the jump exponentially converges to the identity, so it turns out we can truncate it. So we're going to actually use finite segments, which we truncate at 2.5. So I'll just plot these as I add them. So there's one segment. Let me turn off the... All right, and now let me add the other 4. 3 pi, so there's 2, and then let's just add the last 2. Minus 3 pi, and then finally, so here I've defined my contour gamma in fairly readable syntax, at least readable to me. But I mean, it basically looks like mathematic notation, so I assume everybody can read that. Now I want to define the jump. So this is define the contour. Now I want to define the jump.
Your segments are orientated, that's why you have the arrows, so you know your left and right.
Yeah, exactly. Because we have left phi plus, because we're not assuming we can divide it into different sectors, we have to be a little careful about what we mean by phi plus and phi minus. Okay. Okay, so now we define the jump. I'm just going to take x to be equal 0. Maybe I should call it s since I was calling it s before. And then I just define the jump like this. If s is in the first component of gamma, then the jump is 1, 0. I times x of theta of s. Oh. 1, else if s is in the second component, I think it's just a minus sign there, else, well, if it's in the third, then we have the upper triangular version. And then if it's in the fourth, we have, so I think that should be minus, oh, and I forgot that. Okay, so that looks pretty good. So this is just creating the jump on the contour gamma. Okay? It has some, it's expanded it in some Chebyshev expansion. We don't need to worry about that. It's just got some representation for this function on the computer. And now we have the jump. We can say solve the Riemann-Hilbert problem. Now, since this is right Riemann-Hilbert problem, and usually I've implemented the code for left Riemann-Hilbert problems, we actually have to transpose everything and transpose back, but that's not that big a deal. This is sort of a discretization parameter. I'm saying discretize with 400 collocation points. I'll get to that in a second. And then that solved it. And now we can evaluate this, say, anywhere in the complex plane, and it should be accurate to roughly machine precision. So for an estimate of how accurate this is, it should, okay, so to 10 digits, let's say. Okay, and then finally we can, so this has given us a solution to the Riemann-Hilbert problem. We could check the jump if we wanted to. So for example, 1 plus m minus eps, this is phi plus, minus 1 plus m plus eps times g of 1 plus m is roughly 0. Okay, so we've numerically recovered a function to roughly 10 digits accuracy that solves the Riemann-Hilbert problem. And then once we have that, we can actually take the limit at infinity. Okay, so whether you believe me or not, this is the solution to this nonlinear ODE evaluated at x equals 0. But there's nothing specific in this code to this problem. You could have write your own contour, write your own jumps, say solve. And as long as it's numerically well posed, it's probably going to work Okay.
Is the function, so you define the jumps as a finite thing, but then the solution you've actually extended the whole plane?
The phi exists everywhere off gamma.
Oh, sorry, you said phi of 1, 2.
Yeah, 1, 2 means the 1, 2 component of, because,
Oh, okay, but you're still evaluating the function at infinity there.
yeah. Well, I'm multiplying by z and taking the limit. So you multiply by z, phi 1, 2 of z, take the limit at infinity. Okay,
How
because,
does that deal with the fact that the contours are actually only like not that long?
well, because this function is because they're finite contours, it's actually analytic in the neighborhood of infinity. So.
No, I'm just wondering about the implementation. Has it actually like defined it out like beyond the domains of what you just defined there?
Phi exists implicitly as a, well, okay, so phi,
Defined everywhere off the contour, all the way to infinity.
No, but on the computer though, I mean.
yeah, so,
The segments are long, but they're finite.
so maybe I'll show you what's going on behind the scenes. So, phi is written as the Cauchy transform of, sorry, this is getting to the next part of the talk. Phi is written as some Cauchy transform of some function on gamma. Oh, sorry. Blah, 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 blah. Well, I probably need to multiply it by 2 pi I, but okay, so this is the idea, is that we're writing, so this is, we're encoding the solution as, let's say, 2 plus m. 2 plus m, and then probably I need to multiply by 2 pi I, or maybe divide. Yeah. Oh, well, okay, I can't remember. Well, okay. Okay, so still just another normalization for Cauchy transform. Okay, so we're representing the solution as the Cauchy transform of a function defined on gamma. And so essentially everything comes down to how do you represent functions on complicated contours like this, and how do we calculate Cauchy transforms on contours like this. Okay. So let me, maybe I can give an outline of the rest of the talk between today and tomorrow. So part 1 is going to be, I'm going to discuss Cauchy transforms because that's sort of the key thing, and the Plumage theorem. So essentially we're going to think of Cauchy transforms not as their usual integral formula, but in terms of Plumage theorem, which allows us to get sort of non-classical results that are very useful for the numerics. The second part is going to be on Cauchy transforms and orthogonal polynomials. So we're going to see how, so in the end we're going to have a function defined on gamma. We're going to approximate it using orthogonal polynomials. We'll see how doing that leads to very accurate evaluations of Cauchy transforms. 3 is, so probably I'll do 1 and 2 today. 3 will be on oh, no. I'm going to, so 3 is numerical solution of Riemann-Hilbert problems. So we're going to see how accurate Cauchy transforms of orthogonal polynomials lead to a very accurate scheme for solving Riemann-Hilbert problems. 4, this is sort of a bit more on the analysis side, but it's useful for the numerics too. Is something called Dijkstal steepest descent. Now, if we see in these two Riemann-Hilbert problems, we have a jump that becomes more and more oscillatory as, say, x becomes large, or x and t become large, which would destroy the numerics. Dijkstal steepest descent is a way of deforming these Riemann-Hilbert problems through passive steepest descent, just like you would do with integrals. and therefore get accurate numerics even when you have high oscillation. Okay. And 5, I might say something about Sommerfeld radiation, but hopefully I'll run out of time because whatever I say will probably be wrong and there's experts in the audience. Okay. So the starting point is Cauchy transforms and Plumage. So what's the Cauchy definition of the Cauchy transform over contour gamma is just the usual thing. I'm going to use this notation C gamma f of z define equal 1 over 2 pi I integral of gamma. I guess I'm using S. Okay. And the key point is is we can think of it as a transform from functions f defined only on gamma to functions analytic off gamma. So C takes functions on gamma to analytic functions off gamma. Okay. It also has, I'll just define this notation now, it is C plus gamma. So if we think of our contour gamma, the Cauchy transform is analytic off it. Provided f is nice enough, we can talk about left and right limits. And then I'll just call that C plus f of S and C minus f of S. Okay. Now, being an integral, you might think, well, I know how to calculate Cauchy transforms numerically. That's pretty easy. You just use quadrature. So if you wanted to do this numerically, you might say, well, 1 over 2 pi I integral gamma f of S over S minus z ds is approximately whatever your favorite quadrature rule is. You use m points, f of wj, f of sj over sj minus z. Okay? But anyone see what the problem with doing this is? Yeah, exactly. So we've replaced the function, which has a nice clean branch cut, or jump, or whatever you want to call it, by something with poles. So instead of getting the contour, we get a bunch of poles at our quadrature points. Okay. So we're not going to, for the most part, we're never going to think about Cauchy transforms as integrals. Maybe I can turn off the screen now. So instead, we're going to use which could be thought of as a different formulation for, or different definition for the Cauchy transform. We're going to use Plumage theorem. So this is a theorem. I usually call it Plumage 1 because there's going to be a Plumage 2. Suppose we have a function defined on gamma. We're never thinking of f functions defined on gamma. We're never thinking in terms of analytic continuation. They're only defined on gamma. And let's just say, I'll be vague here and say it's a nice function. It can be, say, a few times differentiable, but allowing, say, Jacobi singularities at the left-right endpoints. Okay. then the Cauchy transform of f satisfies the following properties. One, it's analytic off gamma. Two, it decays at infinity. Three, it has weaker than pole singularities. So it may, for example, blow up at the left and right endpoint, but it's not going to blow up faster than 1 over z. Okay, and 4, it has a simple jump that the limit from the left minus the limit from the right is equal to f of s. Okay. Let me just do a brief sketch of property 4 so that we can convince ourselves that this is true. Now, if f were analytic in a neighborhood of gamma, I think the proof is basically follows from it was given in the last lecture. But here we're not allowing f to be analytic in the neighborhood, so we can never deform the contour to establish this. Let's just take gamma equal the unit interval for simplicity. Okay. Well, then the result is pretty straightforward, which is we can write the Cauchy transform as in this way. So we think of it as so here in my mind I'm thinking of here's minus 1, 1. Here's a point z. We're going to let z approach minus 1, 1 from above or below. Plus f of real part of z. So real part of z is just a projection down to here. So we're allowed to evaluate f at real. We're not allowed to evaluate f at z. We can evaluate at f at real of z. And then this is just Cauchy transform of 1. Okay, and then we right away get c plus f of x minus c minus f of x. Well, this term, provided f is sufficiently nice, is continuous as z approaches minus 1, 1. So these terms cancel. All we're left with is f of real part z, which is just f of x times c plus 1 of x minus c minus 1 of x. Well, this is now a nice analytic integrand. It's pretty easy to see that that's just 1. Okay, so the Cauchy transform has this property that the difference between the left and right limit gives us back f. Okay, and this has nothing to do with f being analytic. Yeah, so here I'm sort of implicitly assuming it's finite. It's true if it's infinite, but you just have to be more careful of what you mean by f being nice. It's well, I mean, it's sort of obvious that it applies for infinite contours because you can write the infinite contour as a sum of a finite contour plus things away from x. So provided those integrals make sense, you always have the jump. So it's actually not that complicated.
But in the books, they always take it for finite contours.
Yeah, you just have to be slightly careful, but not that careful. Maybe like f decaying like 1 over x is sort of enough. Or even f decaying like 1 over square root x, because we actually need that for the Wiener-Hopf example. Okay. So what's the second part? If phi, so now we're not assuming phi is the Cauchy transform. If phi is any function satisfying properties 1 through 4, so if phi is analytic off gamma, if phi decays at infinity, if phi has weaker than pole singularities, and phi has a subtractive jump, then it has to be the Cauchy transform. Okay. So this is the important part, is that we don't need to think of these as integrals. We don't need to think about deforming contours. All we need to think about is coming up with a function that's analytic and has the right jump, and that is guaranteed to be the Cauchy transform. Okay. And this is pretty easy to see. You just take now, I'm being very, by theorem, I'm being a bit vague in how I state things, because to state this precisely, you have to talk about angles of approach and various things, which I don't want to do. But the sketch is, if we take the difference of phi and c, then the jump it satisfies on our contour is 0. That means this is continuous on gamma, analytic off gamma, bounded at infinity, and the only way you can have a function that's continuous on a contour and analytic near that contour is if it's analytic on the contour itself. So therefore it's entire, and Liouville theorem implies that it's 0. So the difference between these is 0. That means the Cauchy transform has to be phi of 7. Okay.
In the previous remark, if we don't have enough decay at infinity, then this might be a constant or a polynomial.
Well, they always decay at infinity.
Oh, okay.
So as long as it's entire and decays at infinity. But that's easy to see when gamma is finite. If gamma is infinite, you need to be a little bit more careful. But okay. All right, so maybe I just do I'll do one easy example. Now there's plenty of other ways to work out what the Cauchy transform on, let's say, minus 1, 1 of z is. But we can use this to verify it by just showing that this right-hand side has the right properties. So let's call this phi of z. Okay. So 1 is this analytic of minus 1, 1, Well, you have to be a little bit careful because these both have branch cuts and negative real axis, but for x less than -1, we have phi plus x minus phi minus of x is equal to log 1 minus x plus I pi minus log minus 1 minus x minus I pi plus dot 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 is equal to 0. So therefore, phi plus minus phi minus is continuous, and therefore it's analytic everywhere off gamma. 2, does it decay at infinity? Well, it might not be immediately obvious, but it's pretty obvious that the log terms cancel, and we get decay at infinity. 3, it definitely has weaker than pole singularities, and 4, well, phi plus of x minus phi minus, for x between -1 and 1, we get log 1 minus x plus I pi, and then we get the other contribution, so yes, we get back just 1. Okay, so because this phi of z satisfies these 4 properties, it has to be the Cauchy transform of 1 over z. So now, wait, where am I going? Okay, so why is this useful? Well, it's useful because we can use it to derive change of variable formulas for Cauchy transform that do not follow from classical integral results.
So in that example, do you need to specify f of s before you start?
This example.
Yes.
Well, it's sort of because I'm trying to say that it's the Cauchy transform of 1.
Yes. Okay.
Yeah. So here f is 1. Okay. So this is useful for doing change of variable formulas. So let's say, for example, we want to be able to map domains. Okay, so we could have, say, -1, 1, which we want to be able to map to some other contour. Doesn't really, gamma. What do we want? We want to be able to write Cauchy transforms over gamma in terms of Cauchy transforms over -1, 1. 2, change of variable formulas are also useful for regularizing behavior. So for example, function on R decaying like 1 over square root x can be mapped to smooth function on -1, 1. Okay. So let me just give 3 examples of these formulas, which are not necessarily, which don't follow from standard integration rules, but follow immediately from Helmholtz. So if we have a Mobius transformation, So for example, let's say we have minus 1, 1, which we map to an arc by I minus x over I plus x. Can we recover the Cauchy transform on an arc from the Cauchy transform on minus 1, 1? So this is a function m that takes us from minus 1, 1 to arc. Well, yeah, the answer is yes. The Cauchy transform on the arc is equal to the Cauchy transform of minus 1, 1 of f circle m, so m takes us from x to there, of m inverse of z, minus wherever infinity gets mapped to. Okay, so why does this follow from Plumage? Well, first, is it analytic of gamma? Well, because it's a Mobius transformation, yes, we can confirm that it's 1 to 1, and therefore this right-hand side is analytic of gamma. Does it decay at infinity? Yes, because we subtract off at infinity, so as that goes to infinity, that cancels with that. Does it have weaker than pole singularities? Yes, because this is not going to increase any poles. And does it have the right jump? Well, yes, because if you take the limit from the left here, you get the limit from above there under the map. So when we take the difference, we get f circle of m evaluated at m inverse of s. We get back f of s. Okay.
The last bit is just adding on a constant to make sure the point of infinity goes to 0. That's what you're doing.
Yeah. Okay. So that's a pretty simple example. Let's do a more complicated and more fun example. What if we have a non-invertible map, like a polynomial map? So we have p of x is equal to p naught plus p1 x plus pd x to the d. And well, polynomials are really good at approximating arbitrary functions, including arbitrary curves. So this is really, we can take an arbitrary curve and construct a polynomial approximation of it. So p takes us from minus 1, 1 to this curve. Then the Cauchy transform on gamma, so gamma is the map of minus 1, 1. Well, it's going to look very much like this, except what do we do about the inverse? So if this is our z in the sort of gamma plane, well, there's not going to be one inverse because we're inverting a polynomial. There's going to be d inverses. So we're going to have, say, here's one of the inverse, p1 inverse of z. Here's, say, another one. And there's going to be precisely d of them. So each of these points, when we apply p, the polynomial takes each of these points to the same point. So in a bit of sort of luck, I just tried, well, what if I just sum over all the inverses? I plugged it into the computer, and sure enough, the Cauchy transform on this map domain is just the sum over all d inverses of Cauchy transform of minus 1, 1, f circle p of pj inverse of z. Okay. Now, and again, this follows immediately from Plumage. So as z goes to infinity, all these points go to infinity, therefore both the left and right vanish. Analyticity takes a little bit of work, but it's true that this right-hand side is analytic off gamma. So I did it by writing it as basically using functional calculus and writing it in terms of companion matrices, but that's, I'm not going to go into that. Does it have the right jump? Well, let's assume P is 1-to-1 on gamma. Then you have sort of a unique inverse, and then you can sort of show by the same argument there that this, when we take the limit from the left minus the limit from the right, gives us back F. Okay.
But if you've not taken all of the sum, and if you've taken this without one of them, then wouldn't you get sort of branch cut?
Yeah, exactly.
Yeah.
So, yeah, maybe I can. So the branch cuts sort of magically cancel each other out, and you can see it by writing it as a trace of sort of the inverse of a analytic matrix, but because these correspond to sort of eigenvalues of a companion matrix, and summing over a function evaluated at eigenvalues is the same as trace of the matrix function, and you can use that to show that it's analytic. Okay.
So what happens when you have a quotient of two arbitrary polynomials?
So a rational function that should work too by the same logic. You would just have to subtract off infinity.
So
But that's
one thing, you don't have to subtract.
yeah. I think you have to just. This term will always satisfy the right jump, and then you just subtract off this term evaluated at infinity. But so the last example is an example of this. So this is in a very recent paper by Elena and Stefan Luan-Smith, is here's a rational map which takes us from -1, 1 to R. Okay, so we can write, our goal is to write the Cauchy transform over R in terms of a Cauchy transform of -1, 1. Why would we do this? Well, this blows up like 1 minus x squared as x goes to 1. So if we have a function that decays like 1 over square root x on the real line, when we map it to the -1, 1, we get something smooth. So that's sort of the example of number 2. Okay. So I'm not going to write down, you can write down explicitly the 4 inverses. Again, they have sort of ugly jumps, but the result is, provided F is suitably nice, the Cauchy transform of R is equal, so this has 4 inverses, Cauchy transform of -1, 1, F circle R. This has turned something with square root decay into something smooth, Rj inverse Z, minus, then we just have to kill off the behavior at infinity. Okay. So what this has shown is that provided we can do Cauchy transforms of functions on -1, 1, we can do Cauchy transforms on lots more complicated contours. We can do Cauchy transforms of functions with exotic decay rates, all using these sort of mapping formulas that map us back to -1, 1. Okay. So we basically reduce everything to just how do you calculate the Cauchy transform on -1, 1 numerically. So this gets us to part 2, orthogonal polynomials. So the idea is don't do quadrature. Instead, what are we going to do? We're going to expand f of x in orthogonal polynomial expansion anyone want me to define orthogonal polynomials? I probably don't need to, but so these are orthogonal with respect to the weight w of x. So integral -1 w of x, pk of x, pj of x dx is equal to 0 if k is not equal to j. And we're not necessarily using orthonormal. Okay. Now there's very good numerical schemes for expanding functions in orthogonal polynomials. Maybe I should mention the classical examples is Legendre, which just has the weight 1. Chebyshev, which has the weight for both these and, in fact, any Jacobi polynomials, we can very efficiently, given f, we can very efficiently calculate the fk so that this is a good approximation. So I guess I mean we're approximating f by this weighted polynomial approximation. This converges very rapidly if f is smooth. Well, smooth times this weight, and it's very nice. All right. So how does this help? It helps because we've reduced the problem of calculating Cauchy transforms of functions on -1 to calculating Cauchy transforms of weighted orthogonal polynomials. So the Cauchy transform of f of z is now approximately sum from k equals 0 to m minus 1 Cauchy transform of w pk of z times fk. Okay. Yeah. I don't write the gamma if I can't be bothered to. So for now, because we said we can reduce everything to -1 for now we're just assuming it's -1. Okay. So how do we calculate these? Well, it turns out the Cauchy transform of orthogonal polynomials essentially solves the same 3-term recurrence that orthogonal polynomials do. So it's sort of well known that orthogonal polynomials satisfy a 3-term recurrence. So if we multiply x times our polynomial, we can write this in terms of pm minus 1 of x plus an pn of x plus bn pm plus 1 of x. Okay. What about the Cauchy transform? It satisfies, well, n equals 0 is a special case. Not that special, but let me simplify my notation. Let's define Cn of z as Cauchy transform Pnw of z. Okay. Equals A naught C0 of z plus B0 C1 of z minus 1 over 2 pi I integral minus 1, 1 w of x dx. Okay? So in other words, we know C1 of z in terms of C naught of z and some constant. So if we know C naught of z, we already know C1 of z. Similarly, for n greater than 0, it just is literally the same thing. Unfortunately, I have two c's, so I need to write this c very small and this c very big. Okay, so if we know C naught through Cm minus n of z, then we also know Cm plus 1 of z. Okay. Okay. So for example, if we want to know the Cauchy, before I erase it, if we want to know the Cauchy transform of Legendre polynomials, we use the fact that we know the Cauchy transform of P0, it's just that log thing there. And then we know integral minus 1 to 1 is 2, so we know that term. And then we find out all Cn of z from the three-term recurrence. Okay. So this works for any orthogonal polynomials. If you know C naught of z and you know the integral of the weight, we know the Cauchy transforms. When am I supposed to stop?
5 minutes ago.
Okay.
That's okay, everyone's overrun.
Yeah, everyone's overrun. All right, so let me just make one last comment in terms of stability. So we can write this recurrence relationship in terms of essentially in terms of a forward recurrence in the system. Okay, so essentially we're solving this system with forward iteration, but it's unstable if z is far from minus 1, 1. So this actually works great for evaluating Cauchy transforms on minus 1, 1, or if you're suitably close, and suitably close depends on n. But as we go further and further away, the Cauchy transforms are actually getting very, very small. It's picking up the sort of growing solution to the three-term recurrence, and so therefore it's unstable. Fortunately, there's a way around this, which is conveniently enough called Olver's algorithm. So use a different Olver though. So what's Olver's algorithm? This is for finding the minimal solution to a 3-term recurrence. And instead of solving it as a forward recurrence, you solve as a 2-point boundary problem. So we sort of drop this and okay. And essentially, you can solve this using an adaptive Gaussian elimination, and it successfully, maybe it's not clear, but if you look at just this part, that's the Jacobi matrix, J minus at I. Because we're off the spectrum of the Jacobi matrix, we sort of know this is invertible in L2, and therefore we can think of this as sort of like inverting a nice operator. And you could do finite section, or you can use sort of adaptive Gaussian elimination. But we can very efficiently calculate Cauchy transforms. So basically, we have -1, 1. Inside, we use forward. Outside, we use Olvers. Okay. And essentially, we get the Cauchy transform to machine precision. Okay. So I guess I should stop there.